is lesson 5-7, describing number patterns. There are 6 very important vocabulary words that you need to make sure you copy into your notes here. The first one is inductive reasoning. Inductive reasoning is making observations, finding a pattern, and making a generalization based upon that pattern. For example, weathermen always use inductive reasoning. They look at the weather charts, they look and see what's happening, they find the patterns when they look at the weather charts, and then they make a generalization based upon those patterns. To a certain degree, predicting the weather is really, really difficult because there are so many different things that can change the weather. For the most part, in certain parts of the country, it's really easy to predict the weather because the patterns stay consistent. The Northwest is a very difficult place to predict the weather, which is why a lot of times they cannot always predict whether we're going to have snow or not. A conjecture is a conclusion based upon inductive reasoning. Okay, for example, if I notice that every time I get on the bus, all the girls sit in the front and all the boys sit on the back, if I notice this on the first time I get on the bus, and then the second time I get on the bus, and then the third time I get on the bus, and the fourth time I get, and every time I get on the bus, let's say I get on the bus 25 times, and every time I get on the bus, all the girls sit in the front and all the boys sit in the back, I can make a conjecture that the boys are supposed to sit in the back of the bus and the girls are supposed to sit in the front of the bus, and maybe there's assigned seats. A sequence is a number pattern. Any kind of number pattern you want, like 1, 3, 5, 7, 9. That would be counting by odds. That would be a sequence. A term is each number in a sequence. In the number pattern 1, 3, 5, 7, 9, the first term is 1, the second term is 3, the third term is 5, the fourth term is 7, and the fifth term is 9. It's just a number in a sequence. An arithmetic sequence, sometimes pronounced arithmetic, but an arithmetic sequence is a sequence found by adding a constant number to each previous term. The above is a arithmetic sequence because if I look at this, I'm adding 2 here, I'm adding 2 here, I'm adding 2 here, I'm adding 2 here. There's a constant difference, and that constant difference is 2. Okay? The constant number we're adding to the previous term is 2. That's called the common difference, the fixed or constant number. And so this makes this an arithmetic sequence. And we can work with arithmetic sequences and do some things about them. We're going to look at these sequences here, and we're going to use inductive reasoning to try to find a pattern and then find the next 2 numbers within the sequence. If we look at this, 1, 5, 9. Well, 1 to 5, you're going to add 4. 5 to 9, you're going to add 4. So my inductive reasoning tells me that we're going to add 4 to the previous term. So if I was going to describe the number pattern, I would say add 4 to the previous term. And you have to say, yes, previous term. You can't just say add 4. So if this pattern were to continue, 9 plus 4 is 13. 13 plus 4 is 17. If we were to look at the next pattern, we might say, well, this would be adding 2, and this would be adding 6. Well, so we can't say adding. So adding is definitely not in this pattern. Maybe we need to multiply something. If I look at this, 1 times 3 is 3. 3 times 3 is 9. I would say you're going to multiply the previous term by 3. So if I was to continue that pattern, 9 times 3 is 27, and 27 times 3 is 81. Last pattern here, 1, 4, 9, 16. Okay, you might look at this and go, okay, this is adding 3, this is adding 5, this is adding 7. And you're like, well, you're adding odd numbers, but that doesn't seem like it's a really good pattern. You know, you could say add consecutive odd numbers, but that's a really hard pattern to do. So I want to see if there's a different pattern I can find here. So I might look at this. The difference between 3 and 5 is 2. The difference between 5 and 7 is also 2. So there's got to be a 2 in this pattern somewhere. I know what this pattern is, so it's really easy for me to pick up on it. I happen to know that the next number in this pattern is going to be 25. I know the number after that is going to be 36. And it's not because I looked at this and said, oh, I'm going to add 11 and then I'm going to add 13. You could do that, but that's a really hard pattern to look for. Because if I asked you for the 20th term, you're going to have to do 19 terms in front of that. That's kind of hard. A better thing to look at is to look at this. If I look at this, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. So it's basically the square of the term. They're squares of consecutive numbers. So that would be the best pattern to say, squares of consecutive numbers. So obviously, if you look at this, A is an arithmetic sequence, B and C are not arithmetic sequences. We're going to look a little bit more in-depthly at arithmetic sequences for just a couple of minutes. Okay? I've told you that these next 3 sequences are arithmetic sequences, so we need to find the common difference. So in other words, we need to know what they are doing. If we look at the numbers -7, -3, 1, and 5, to go from -7 to -3, you're going to add 4. You go from -3 to +1, you're going to add 4, and 1 to 5, you're going to add 4. So the common difference is 4. Fairly simple to do. You're going to add 4. When you look at the next one, 5 to 2, you're going to subtract 3. 2 to -1, you're also subtracting 3. 1 to -4, again, you'll subtract 3. So the common difference is -3. Because remember, your common difference is always what you're going to add. Add 4, I'm going to add a -3. 8 to 11, I'm going to add 3. 11 to 14, I'm going to add 3. 14 to 17, I'm going to add 3. So my common difference is 3. Now you can use the common difference of the terms of an arithmetic sequence to write a function rule for that sequence. You need the first term, whatever term number you're looking for, and the common difference to find the value of any term. And it's given by the following formula. An arithmetic sequence is found by taking a of n, which means whatever term I'm looking for, whatever the nth term is equal to a plus n minus 1 times d, where a of n is the nth term, small a is your first term, n is your term number, and d is your common difference. Okay, for example, let's go back to this letter A up here. If you look at letter A, it had the numbers -7, -3, 1, and 5. So let's just write that down. -7, got already, 3, 1, and 5. We found that the common difference was we had to keep adding 4, didn't we? So my common difference is 4. So in this particular case, d equals 4. My first term is -7 right there. So my first term is -7. My term number is just going to be n. So I can write a rule for this particular sequence. And my rule would be a of n, which means whatever term I'm looking for, is going to equal -7, because that's my first term, plus n minus 1, whatever the term number is, times 4. So we already have 4 terms. The 5th term here should be 9, shouldn't it? Because we add 5 plus 4, we'll get 9. This term right here should be 9. Let's see if we actually get that if we're looking for the 9th term here. Because if I was going to look for the 9th term, I'm looking for a of 9. N becomes 9. That's going to be -7 plus 9 minus 1 times 4. So if I was to plug that in, that's going to be -7 plus 9 minus 1 is 8 times 4. So that's going to be -7 plus 32. 32 plus 7 is going to equal, we're looking for, oops, I'm not looking for my 9th term, I messed up. It's okay, we'll figure this out. 32 plus -7 is 25. So my 9th term of this sequence should be 25. Okay, my first term was -7, my second term was -3, my third term was 1, my fourth term was 5, fifth, 1, 2, 3, 4. This is the 5th term, 6th term, 7th term, 8th term, 9th term. If I kept the pattern of adding 4, 5 plus 4 is 9, 9 plus 4 is 13, 13 plus 4 is 17. 17 plus 4 is 21, and 21 plus 4 is 25. My ninth term is indeed 25. So it does work once you've figured out the pattern. The glorious thing about it is once you understand this rule, you don't have to find the preceding 8 terms to find the ninth term. Right? So we're going to apply that by finding the second, the fifth, and the ninth term of each one of these sequences above. Right? So all I'm going to do is find the missing terms. So in other words, n is going to equal 2, then n is going to equal 5, and then n is going to equal 9. So my second term is going to be negative 5 plus 2 minus 1 times 3. So that would be negative 5 plus 1 times 3. So negative 5 plus 3, which happens to be negative 2. So my second term is negative 2. My fifth term, a of 5, will be negative 5 plus 5 minus 1 times 3. So negative 5 plus 4 times 3, negative 5 plus 12. And negative 5 plus 12 happens to be 7. So my fifth term, a of 5, equals 7. And last but not least, we need to find the ninth term. So a of 9 will equal negative 5 plus 8 times 3. 8 times 3 is 24. Negative 5 plus 24 happens to be 19. So those are my 3 terms, my 3 missing terms of that particular one. Now I can find my next one here. A of n equals 15 plus n minus 1 times 5. Again, finding my second, my fifth, and my ninth term. So a of 2 will equal 15 plus 2 minus 1 times 5. So 15 plus 5, which equals 20. A of 5 will equal 15 plus 5 minus 1 times 5. So 15 plus 4 times 5. 4 times 5 is 20. 20 plus 15 is 35. And then a of 9 equals 15 plus 9 minus 1 times 5. So that's going to be 15 plus 8 times 5 is 40. And 40 and 15 is 55. So my 3 terms are 20, 35, and 55. And you can do that with this last one, but I'm just going to choose not to do it at the moment. As you can clearly see, sequences aren't that difficult. Okay, I could ask you to write a sequence, okay? Write a rule if I gave you certain things. Okay? You could write a rule if I gave you a sequence. We did that on this page here when we wrote the rule for the sequence of negative 7, negative 3, 1, and 5. You can go that way, and then of course you can apply it by using the rule this way. That's all there is to know about arithmetic sequences at this point in time.